So, welcome back. Let us start with lecture 16. So, in last lecture, we have seen matrix representation when we use x, y, z coordinates or orthogonal set of coordinates. We transform orthogonal set of coordinates. So, now let us see if we can use the same principle to develop matrix representation for a point group. So, matrix representation. So, we will see here when our symmetry operations lie along axis systems or the orthogonal coordinate system, it is much easier to write a matrix representation. And so we will take both examples where the uh, symmetry operations lie are along the axis system and where it does not lie, so that we'll cover both the cases. And then let us take an example. So let's start with water molecule where the point group is C2V, and we know the symmetry operations or the group elements in this case are E, C2, we'll say Z, sigma XZ, and sigma YZ, right? So in this particular case, let us call this representation. So now I am not writing a group multiplication table, but the format of writing is similar. So here on the left hand side, I'm using a symbol tau, and I'm using the basis set. Basis set is the set of vectors which are chosen for defining a particular matrix. Okay, so in this case we have chosen xyz, so I'm writing tau xyz. So now let us see what do we have in place of E. What matrix do we have? So we know that E does not do anything, and it has to be 3 cross 3 matrix because we have 3 bases in this. So it has to be a unitary matrix of order 3, right? So again, to remind you, if I am doing this operation E onto xyz, I am getting xyz back, right? So that tells me that my E is nothing but a identity matrix of 3 cross 3. Now in same way, if I'm doing C to Z, we have seen how to develop a rotation matrix. So we have cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, right? So we'll just say theta is 180 degree in this case. So let me just write down C2Z we defined as not C2Z, let's write CNZ cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. This was done in last lecture, right? So any rotation by 2 pi by n where theta is equal to 2 pi by n, right? So in this case our theta will be pi, right? Because n will be equal to 2. So 2 pi by 2 will be equal to pi. So we will have these values. So this is very easy because our rotation axis is lying along one of the axes, right? So let's continue with this. So cos pi, what is cos pi? So I leave it for you. Cos pi, sin pi with a negative sign 0. Then we have sin pi, cos pi 0, 0, 0, 1, right? Now let us see what happens to sigma xz and sigma yz. So that also we have seen sigma xz means the only y goes to negative. So if I am doing this operation sigma xz onto x y z, what I will have is x will remain as x, y goes to minus y, z remains as z, right? So I can say that this is 1 0 0 0 minus 1 0 0 0 1. Similarly in case of sigma yz, x will be negative 0 1 0 0. So this is a very straightforward way of writing a representation in terms of a matrix where we are using orthogonal coordinate system as our basis sets, right? And fortunately, our symmetry operations are lying along those axis system. Now let us look at an example of NH3. So NH3 is a C3V point group, right? So let's draw the axis system. So let's say if we have nitrogen at the axis and this is along YZ plane, H, H. So if I'm looking from the top, because I'm not really interested in Z is not going to change. So let's just look at it in 2D format. So it will be easier to understand. So this is my nitrogen. One of the, let me draw the bonds with red color. So one of the NH bond is actually lying along YZ plane. Another one is somewhere here. And this one is somewhere here, right? So now you see it is not, these two bonds are not lying along XY system, along the coordinates or along the planes. So it will not be straightforward as was in the case of water to write the matrix representations. So let us see how to do that. Okay. So let's start with writing C3V. So again it is tau xyz. So I'm not going to write for E because again E will be the 3 cross 3 I matrix. So let's start with C3. Okay. So C3 in this case will still be okay because C3 is lying along Z axis, right? So C3 will still be cos, will still go with the same formula, just that the angle will change. So in this case it will be 2 pi by 3. So cos 2 pi by 3 minus sine 2 pi by 3 0 sine 2 pi by 3 cos 2 pi by 3 0, and you can see this will be 1 by root 2 minus root 3 by 2 0 root 3 by 2 1 by root 2 0 0 0 1, right? Similarly, you can also write for C3 square because again C3 square is lying along the Z axis, so writing the C3 square will be easy. So I must also tell you that C3 square is a inverse of C3, so you can just transpose this matrix and write for C3 square, right? Why will see in a minute. So the minus sign comes here, cos 2 pi by 3 0 0 0 1. So I said C3 square is inverse of C3, and in this case the inverse can be written as simply C3 square is equal to C3 transpose. By transpose I mean changing the rows into column and columns into rows. Why is that? Because this is a orthogonal matrix. So for orthogonal matrix, the inverse, if A is an orthogonal matrix, we can say that A inverse is equal to A transpose. Okay, where we can say A inverse A is equal to I, or E in this case, right? So why it's an orthogonal matrix? Because our basis sets are X, Y, Z. So that makes this rotation matrix as an orthogonal matrix. So this is true for all orthogonal matrices, that the inverse can be written as transpose. So we can simply transpose it and get the inverse. Now let us write for sigma. So again, writing for sigma is easy for 1, sigma 1. We have sigma v1, sigma v2, and sigma v3, right? So let us see one by one how to write for different sigmas. So for sigma v1, we know that it is lying along yz plane, right? We can see that here. So because it is lying along sigma yz plane, so we can say that this is equivalent to sigma v yz. And we have seen that in the case of water, how to write for sigma yz. So only x becomes negative and rest of the elements are same as E, right? Because y and z does not change in this. So that is again easy. Now let us consider the difficult case of sigma v2. Okay, how to write this one? Once we have figured this out, we can write this one very easily from group multiplication table, because we know that the product of these two, or we'll figure it out how to write for sigma v3. Let's first focus on sigma v2. So let me draw this molecule again in the plane. Okay. Now let us mention all the angles. Okay, this angle is going to be, this complete angle is going to be 120. So this will be 60 degree. This will be 60 degree, right? And this complete will be 120. So this will be 30 degree. This will be 30 degree. And we are trying to write for sigma v2, a plane which is actually passing through this NH2 bond. This is my sigma v2, right? Now we have to see, to be able to write this, we have to see how the axis system is changing upon application of the sigma v2, so that we can write the new axis system in terms of old axis system, the way we did it for rotation, and how it changes. So let us see what happens to xy. So if I use this reflection for y comes somewhere around here, because this is NH, this sigma v2 is making an angle of 60 degree with this plane, with this y axis. So we can say that the y will be going somewhere here. Let's call it as y prime, right? Now this angle will be 60. So this will be 30 degree. This complete will be 60, because this was 60, so this will be 60. So it is not to the scale, so you can see that it is not, right? Now what about angle between sigma v2 and x? What will be that angle? Okay, so that angle will be, this will be 30, and this x will be reflected into a new x prime. Let's call it as x prime, and this angle will also be 30 degree, right? This has to be equal to this angle. So again, this is not, the angles are not drawn to the scale. So if you actually draw it to the scale, you'll see that it is much easier to look at. All right. Okay, so now we have defined the new axis system x prime and y prime, which comes as a result of reflection by sigma v2. Now let us try to write down x prime y prime in terms of x and y. So it is easier to see if we can say that x prime, which is this, can be written in terms of x as x cos 60, because this angle is now 60 degrees. So we can say that x prime can be written in terms of x cos 60 minus y sin 60. This is a simple trigonometry, so I don't think I need to explain this. So all you're doing is you're taking a projection of x prime onto x-axis and minus y-axis. So length of this projection will be x cos 60 and this will be minus y sin 60, right? Now similarly we can say that y prime, so this is y prime. Now again try to put the projections onto x and y's original axis system, and this will be equal to, we can say that it is making an angle of 30 degree with x, so we can with minus x, so we can say minus x cos 30, and it's making an angle for minus y, this will be minus y sin 30, right? So we can say, if we want to write this whole thing in matrix form, we can say that cos 60 will be equal to 1 by 2, and let's write down x y, which changes to x prime y prime, similar to what we did for rotation, right? So half minus of sine 60 will be minus root 3 by 2. Now cos 30 will be root 3 by 2 with a negative, and sine 30 will be half with a negative here because negative sign is there, right? So if you see, x and y are changing to x prime and y prime with this relation, right? So this should be the matrix corresponding to sigma v2, and z, we can now include z. So z does not change because z is lying along this plane, so z does not change, so we can just introduce it by writing 1 over here. So how do you write sigma v2? So sigma v2 now can be written as, complete sigma v2 can be written as 1 by 2 minus root 3 by 2, 0, minus root 3 by 2 minus half, 0, 0, 0, 1. So this last column and row are added to show that z does not change. So we had already written for sigma v1. Now we also have for sigma v2. Now let's see for sigma v3, how do we write for sigma v3? So can we say that, okay, let's do this operation. So can we write sigma v3 in terms of product of sigma v1 and sigma v2? So let's say if we have NH3, I'm showing it from the top. So if I'm doing sigma v1, I get 3, 2, and if I'm doing sigma v3 will give you NH3, H1, H2, right? So H1 and H2 will be reflected. Now if I want to go from here to here to identify what are the factors of sigma v3, all I have to do is see H3. So I have to take H3 here, right? And then H1 here and H2 here. That tells me it's a C3 square rotation anti-clockwise, right? So if I'm doing C3 square rotation using this, so I can write it like this, that sigma v3 is equal to sigma v1 followed by C3 square, right? So we already know what is sigma v1. We know for sigma v1 is here, we know for C3 square is here, so we can write the product and basically what it is. So we have cos 2 pi by 3 will become negative, so it is easier to now write. So we have this matrix, we can write as cos 2 pi by 3 sine 2 pi by 3, 0, and then we had C3 square as minus of sine 2 pi by 3 here, minus sine 2 pi by 3 cos 2 pi by 3 0 0 0 1, right? So what I have done is I have just done the matrix multiplication for these two to obtain sigma v3. Otherwise, indirectly you can also write for sigma v3 by doing a axis transformation to by using a reflection along this plane, but which is again will be tedious. You'll have to do the axis transformation, write the new matrix and do this, but it will come out to be same. Okay, so we have now seen how to write matrix representations for a point group where our symmetric operations are lying along the coordinate system and where our symmetric operations are not lying along the coordinate system. Okay, so in the former case it is little easier, like we saw in the case of water, whereas in the case of NH3 or other complex molecules it will be more tedious to write. So how many such representations are possible? Let us ask ourselves. So let's again take an example of water. So let me draw this. Let's say if I change the basis set now to something else. So earlier my basis set was XYZ. So I got a 3 cross 3 matrix representation. Now let's say if I'm choosing this vector V1 and this vector V2 as my basis set. So what I mean to say is that PC2 sigma V1 sigma V2. Let's say tau V1 V2. Now this will be a 2 cross 2 because my basis set has two vectors. So this will be 2 cross 2 identity matrix 0 1 1 0. Now for C2, we see that if we apply C2, V1 will be replaced with V2 and V2 will be replaced with V1. In other words, if we do C2 matrix onto V1 V2, what we get is V2 V1, right? So I can say that this will be 0 1 1 0. Simple to write. Now let's say for sigma V1. So sigma V1, let's say that the sigma V1 is the plane which is reflecting V1 V2. So again it will be V1 will be reflecting V2. So we will have 0 1 1 0. V1 will be replaced with V2 and V2 will be replaced with V1. Now sigma V2 is the plane where all three atoms lie. So the vectors will not move. So basically it will be like identity here. So we can say 1 0 0 1, right? So this is another representation for same molecule but in two-dimensional space where the space is defined by the basis vectors v1 v2. Let's write another representation for water where now the basis set is the s orbitals onto water. So one is A, let's call it as B, one is B. Okay, so if we do that, what do we have? So as you can see, this will be exactly same as above. So again, s orbitals will be replaced with each other in C2 operation. So we have 0 1 1 0. Sigma 1 will also reflect 1s1, so with 1sb. So we have 0 1 1 0 and 1 0 0 1. Let's write one more representation with same molecule. But in this case, now the vectors are actually perpendicular to this plane of water. Okay, so these are the two vectors. Let's call it as vector A and vector B, which are now perpendicular to this plane defined by the water plane. Okay, now in this case, tau AB, this will be again same. Now for C2, what happens? If I'm doing a C2, A will be replaced with B, B will be replaced with A, but in addition to this, their directions will also change. So if I'm doing a C2 rotation, B will come here but with a direction downwards. Similarly, A will come here but with a direction which is downwards. So in such a case, to represent, so what I have to do is I have to write it as negative, right? So 0 minus 1 minus 1 0. So now you can see that the representation from here to here is different. Here the vectors were in plane and parallel to the bonds. Here the vectors are perpendicular to the plane. So it changes. Now let's write for sigma v1. So for sigma v1, it will be A will be replaced with B without any change in the direction of the arrows. So we'll write 0 1 1 0. And for sigma v2, so again sigma v2, A will not be replaced with B, but A will be changed into direction. So it will be a negative unit matrix. So A remains at A but changes its sign by doing sigma v2. Similarly, B remains at B but changes its sign. Okay, so we can say that there are multiple such representations possible. So if we now try to list all the representations down, what we have looked so far, so we have seen E, C2, sigma v1. I'm not going to write all the matrices again, but I'll just try to make a point that, let's say if I have sigma xyz, I get a 3 cross 3 matrix. If I have v1 v2 vectors which were in plane, I get a 2 cross 2 matrix, which is a different representation than the above. Now if I have 1s-A, 1s-B, I get a different representation than above. If I have AB vectors which were perpendicular to the plane of water, I get different vectors. So I can keep on choosing different basis set, I can keep on getting different matrix representations. So how many such representations are possible? The answer is many representations, which is limited by your imagination. So which is limited by your imagination of basis sets which are chosen to carry out the transformation under different symmetry operations, right? So that's all for today. So we will see more of this matrix representation in next class. All right. Thank you.